In this presentation, I expand on what you read about in the Jones and Kotler chapter in regards to inferential and multivariate statistics. So as my prior presentation noted, I'm breaking up my discussion of this content into two presentations. The first one was about descriptive statistics, and this presentation is going to focus on inferential statistics and multivariate statistics. So again, in terms of the purpose behind this lecture and this content, I basically just want you to know enough to be dangerous. So the basics of really reading a results section in a quantitative journal article. This idea of inferential and multivariate statistics, a lot of the techniques that I'm going to discuss, I'm not going to go over the specifics of how they're estimated or calculated or whatever, because that's way beyond the scope of this class. But I want you to be able to be familiar with these so that when you're reading journal articles and learning within the literature in higher education, you understand the basics of what these statistics are. So as I said in the last presentation, I'm going to do my best to make my discussion of statistics straightforward and hopefully also interesting. I really want to emphasize the connection between research questions and then the statistics that people use to answer those questions. So in terms of the types of statistics that are out there. So in my last lecture, I talked about descriptive statistics. So there's univariate statistics, which look at just the attributes of just one measure or variable, right? So for instance, the mean. Then there's also bivariate descriptive statistics, which look at the relationships between two variables. So maybe the correlation between SAT verbal score and SAT math score. And then in this presentation, I'm going to move beyond descriptive statistics to talk about multivariate statistics as well as inferential statistics. So basically, multivariate statistics help us to understand relationships among many variables. So taking the step past the bivariate statistics, which got at the relationships between two variables, and then helping us to understand instead how maybe three or more variables are related to one another. So there are a number of research questions that can be answered by multivariate statistics. Two examples are up on the screen. So first of all, what factors predict the likelihood that a student will graduate from ASU in 4 years? So in this case, our dependent variable of interest would be graduation, right? Completion rates in 4 years. That's one of our variables. But note that the way the research question is phrased, I'm interested in understanding what factors are related to that. So maybe I'll look at, 6 or 7 different likely variables that are probably related to graduation from college. So maybe I'll look at the relationships that gender, race, GPA, student involvement, all of those are a number of different variables, right? So multivariables, so the idea of multivariate statistics, and we want to look at how each of those are interrelated with one another, and then also are uniquely related to graduating from ASU. Another research question that would be answerable with multivariate statistics is what pre-college characteristics are associated with first semester GPA? So again, as we can see here, the dependent variable of interest, our focus here of this research question, is understanding the predictors of first semester GPA, so grade point average. And maybe again, we would want to understand how gender, race, high school attended, maybe socioeconomic status, all kinds of different pre-college characteristics we could draw from existing theories to try to identify some of those likely pre-college characteristics, but then we could run a model that helped us to understand the interrelationships among all of those, and then also how they're associated uniquely with first semester GPA. So that's the conceptual idea of multivariate statistics. It helps us to answer these kinds of research questions that involve more than two quantitative variables. So one of the most common multivariate statistical techniques that is used in higher education research, and if you haven't already run into it, by now, you will definitely see some examples of it when we meet in class in person, but it's called regression analysis. And essentially what regression allows us to do is answer those two research questions that I had listed on the prior slide. Essentially, it's a statistical technique that is used to explain or predict values of a quantitative dependent variable based on values of one or more independent or predictor variables. So that's, kind of statistically, kind of maybe mumbo jumbo in a lot of ways. But the important thing to know is that regression is a very common technique that's used to predict or explain dependent variables. There are a lot of different kinds of regression analysis that you might run into as you're reading through the research. So a simple regression analysis just uses one quantitative dependent variable and one quantitative independent variable. And I'm going to give you an example on the next slide of some of these. A multiple regression is one quantitative dependent variable and then two or more independent variables. So the idea that we're looking at multiple factors that predict something or multiple characteristics as opposed to just one independent variable, one characteristic. Linear regression so there are a couple of different regressions that are characterized based on the scale of the dependent variable. I know this is getting really technical, but I at least want to explain what these are. You'll probably forget it tomorrow, but I just want to explain what they are. So anyways, so linear regression are the techniques that are used for dependent variables that are basically what's called continuous on scale. So either interval or ratio scales. So maybe let's think about SAT score would be an interval dependent variable. What is some other ones? Let's think about it. So income is another one that would be used. We would use linear regression to predict income. If your dependent variable is binary, then you use logistic regression. So logistic regression is essentially to predict, let's say, whether or not someone drops out of college, because that's binary, right? You're either in college or you dropped out. So logistic regression is the regression technique that's used to predict something like dropping out. So continuous dependent variables we use linear regression, and then binary dependent variables, we use logistic regression. Occasionally we'll have multiple categories that we want to predict, and we'll use what's called multinomial regression. So that's when your dependent variable is nominal or ordinal. Let's say we want to predict somebody's major. So major, there are a lot of different categories, right, of major, but it's not on any sort of interval or ratio scale. There's no order to it. So if we wanted to predict major, we would use something like multinomial regression. So I'm going to give you some examples of research questions that get at some of these that are used by some of these different regression techniques. So first of all, a simple regression example. So exactly what I was saying. This research question here, does a student's SAT math score predict his or her SAT verbal score? Is a question that can be answered by a simple linear regression. So why linear regression? So linear because what's our dependent variable of interest here? What's our dependent variable? So in this case, we're saying, does math score predict SAT verbal score? Which one of those two is the dependent variable? So it would be SAT verbal score. SAT verbal score is the dependent variable in this question because we're trying to understand the extent to which it depends on somebody's SAT math score. So math score is the independent variable, and we want to know the degree to which the independent variable of math score predicts the dependent variable of SAT verbal score. The SAT verbal score is on a continuous scale, right? It's an interval scale. So I don't even know what the SAT verbal is today, but it used to be 0 to 800, right? Anyways, so because that scale is on an interval scale, we would use linear regression to predict verbal score. So there's just two variables, one independent variable and one dependent variable. So that means we're going to just use a simple regression. And so I have some output up here. Actually, I'm not going to even explain this at this point in time. Don't even worry about what's on the rest of the screen. This is the Spss output that comes from predicting this relationship using data from the UCLA SERP survey. And this presentation I actually used for my doctoral students who actually had to run this thing. So don't even worry about the output up here right now, but just know that here, a simple regression could allow us to answer this research question right here. In terms of multiple regression, let's say we wanted to know how well do high school GPA and SAT math score predict a student's SAT verbal score. So that is the idea of multiple regression. So the important thing to know here, several things, right, in the way that this differs from the prior simple regression. Okay, so multivariate statistics get at the interrelationships of the variables that we're examining with one another, right? And so they allow us to predict and explain dependent variables. The idea of inferential statistics takes a bit of a different tack. So basically, the underlying question that we're looking at when we're interested in inferential statistics, making inferences, is back at this idea of understanding the degree to which our sample can be generalized to the population. So let me get into some more specifics about inferential statistics now. So like I said, inferential statistics, we want to make inferences about the characteristics of our population based on our sample data. So let's say you actually, in your study, you're doing a quantitative study, and let's say you did, your population of students was residential students on the Tempe campus. And let's say you did a survey of all of the residential students on the Tempe campus, and every single one of them responded to your survey. If your population is completely represented in your data and all the responses you get, you don't need to even worry about inferential statistics because you have a census. You have everybody in your population represented in your sample. However, if, let's say, your response rate of your students to the survey was only 50%, so that would mean that you had your data represented 50% of your population. So what inferential statistics allow you to do is say whether or not the information that you collected, the quantitative information you collected, reflects the population. So I'll get into more specifics here about how we do that. Essentially, we use this statistic that's called a p-value, or it's also called the alpha level, or the confidence level of our ability to say that what we collected, the data we collected from our sample, reflects what exists in the population. So the p-value essentially is the probability that we're wrong, basically that our sample doesn't reflect the population. And so the standard that we commonly use in educational statistics, educational research, is 5%, or of a p-value of 0.05. And I'll get into some examples of seeing those in tables that are reported in real journal articles. So you'll see this. This connection will make sense in a second. But essentially the important thing to know is that your p-value is basically the probability that your sample does not reflect what exists in the population. So it's the probability that somehow maybe you surveyed 50% of the population, but they were, not representing the other 50%. So your p-value is the proportion or the probability that what your data reflects is not accurate to the population. So there are two common types of inferences that we make. First of all, differences between two or more groups on a single variable. An example of that would be, let's say we wanted to compare the mean score on SAT of women compared to men. So we sometimes want to make inferences about the differences between two groups. And there are two techniques that are commonly used to do that. One is called a t-test and one is called ANOVA, or analysis of variance, and those two were briefly discussed in the Jones and Kotler chapter. But essentially the important thing to know is that in one case we want to make inferences about the differences between two or more groups on a single variable. And I'll give you an example from a research study in a second on this. The other type of inference that we want to make sometimes are about relationships between variables. So again, getting at this idea of correlation or partial correlation. So maybe we want to make an inference about the likelihood that math SAT score is correlated with verbal SAT score in the population of high school students or something like that. So either, hopefully this makes sense, either we want to make comparisons of two or more groups, or we want to look at relationships between variables. And the p-value technically is actually just a function of the size of your sample, so the number of people who respond to your survey or the number of cases that you have in your data set, as well as the size of the difference between the two groups, or the size of that relationship between maybe math and verbal score. So again, this is a little bit getting a little technical. I'm never going to have you calculate p-value, but if you're sort of like, what the heck is p-value? Essentially, it's a function of your group size, your sample size, as well as the relationship you calculate between those two variables, or two or more variables. So related to the idea of p-value is a term that we use in social science research that's statistical significance. So maybe you've heard someone say, or you've read somewhere about statistical significance. Essentially, that is when your p-value is really low. So if you think the probability that your sample doesn't reflect your population is really low, that means that your results are statistically significant. So when something's statistically significant, you are saying that you're pretty sure your level of error is low enough that your sample data reflects the population. So oftentimes in tables and in studies, this is indicated with an asterisk or several asterisks in the tables. Stars, those little stars that you'll see in tables, and I'll show you some examples on the next slide, is when you have statistically significant results. Okay, so here's an example. Let's get some examples of this. So this is from an article that was published by Pike in 2000. And essentially he was interested in looking at the influence of fraternity or sorority membership on students' college experiences and their cognitive development. So this is an example of the first kind of inference that I mentioned a few slides ago. So a difference between two or more groups on different variables. So he's interested in comparing Greek students or fraternity and sorority members to non-Greek students. His research questions are up here. They're actually not very well worded. Remember how we talked about how you should try not to word your research questions as yes, no? These aren't great research questions, but he wanted to look at whether or not a conceptual model of college effects can be used to represent observed differences between students' background characteristics, college experiences, and gains in cognitive development. So this research question, he did some descriptive statistics on this. But then the second research question, he was interested in understanding, is this conceptual model, basically the background characteristics, college experiences, and gains in college development, are those variables the same for Greek and non-Greek students? So how did he do this? He did what we call a t-test. So here's his table, and I'll put his whole article up in the supplemental section of Blackboard, but here's the table that he used to report his results to try to analyze research question number 2. So basically what you can do is look at this table, and you see a column here on the left side, or the very far left side, are all of his independent variables. So you'll see that they match to, and he explains this in the paper, his conceptual model, so students' background characteristics, college experiences, and gains in cognitive development. So you'll see up here, the first group are of variables, so gender, female, ACT English, ACT Math, using the library, or actually those first 3 are just the background characteristics that he used. And then the next variables from use of the library all the way through integration of information and conversations are different college experiences. And then finally, he has a bunch of different measures of gains in cognitive development. So I'm sure he administered a bunch of different cognitive tests to his sample of students. So essentially what he did was he sampled, and you can see here, a group of students that were fraternity and sorority members, so Greek students, and then also in his data set he sampled a bunch of students who weren't part of Greek organizations. And then he collected the data on all of those data listed in the left side of the measured variables column. All of those data he reports here underneath the means for Greek students and the means for non-Greek students. So the important thing to know, though, is that some of these differences are statistically significant and some of them aren't. So you see the little stars here next to female, for instance. And if you go down at the bottom of the table, you'll see he has a little guide here to say what the different stars mean. And you'll see down there or the little p's for p-value. So 1 star means that the relationship has a p-value of less than 0.05, so, or a confidence interval of 95%. So essentially that would be, he's saying, we would be able to say that this relationship is observed in the population 95 times out of 100. We only think there's a 5% chance that we're wrong. And then a p-value of 0.01 has 2 stars next to it, so essentially saying that we're 99% sure that what we observed in our sample is reflected in the population. And then 3 stars is a p-value of 0.001, and essentially that says that the relationship that we're observing is, we're 99.9% certain that the population is reflected by what we collected for our sample. And so now if you go back up here to the table, we see that we have our little p-value code up here. So what does this tell us in practice? So let's go up here first of all. So we see 3 stars next to the female variable, right? So that essentially tells us, coming over here to the 2 columns that say Greek and non-Greek, we see 0.91 is the mean for female for Greek students, and 0.71 is the mean for non-Greek students. Essentially, that means 91% of the sample are Greek students, 91% of the sample of Greek students are female, and 71% of the sample of non-Greek students are female. So basically what that tells us is that these differences are, this difference between the Greek students and the non-Greek students on gender is statistically significant, and that in the population of students, there are more females that are Greek than there are females that are non-Greek. So proportionally, there are more women in our population of Greek students than our population of non-Greek students. So going down here, there's no stars next to ACT English. This is also important because if you come over here, you see the mean English score for Greek students is 26.15, and the mean score for non-Greek students is 26.31. So non-Greek students, actually their mean score on ACT English is slightly higher, right, in our sample. However, the important thing about these stars is that that difference is not large enough in magnitude to say that we believe it's actually reflected in the population. So essentially, even though there's a difference in our sample and non-Greek students have a little bit higher ACT English scores, we cannot be confident that that difference is actually reflected in the population. So let's say we wanted to talk about whether or not Greek students and non-Greek students have higher ACT English scores than one another. We would say no, we don't observe any difference in the ACT English scores of Greek students versus non-Greek students. Same for ACT Math. There's no star there, and even if going over here in the column, we see there is a numeric difference in our sample, but again, that difference isn't big enough to be able to say we're confident that in the population of Greek and non-Greek students, there is actually a statistically significant difference. So that's what these stars do. These stars basically tell us that even if there's a difference in our sample, if there are no stars, we can't really say that that relationship or that difference is observable in the population. Let me give you another example in terms of, okay, let's go down here. So let's look at our gains in cognitive development. So we're interested in knowing whether or not Greek students and non-Greek students have different levels of gains in cognitive development. So what could we conclude here? Even if, seeing in these columns the means between Greeks and non-Greeks are different, numerically for our sample, the only cases where there's a statistically significant difference are communication skills, which Greek students actually have higher means on, gains in interpersonal skills, which Greek students also have higher mean scores on, and gains in critical thinking, which Greek students also have higher scores on. So if you look through here, you would say that there are no statistically significant differences in cognitive development of Greek and non-Greek students in general education, in mathematics, and in science and technology. However, this study indicates that Greek students do have higher gains in communication skills, interpersonal skills, and critical thinking. We'll go through some more examples in class, and I'm going to do one on the next slide of a regression example, a regression table. But the important thing to know is that really when you're talking about statistical significance, if you see these different variables and there's no stars next to them, that means that those variables are not statistically significant and those relationships are not observed in the population. Okay, so again, this is an example of the second kind of inference in terms of this helps us to make inferences about relationships between or among different variables. So this example comes from a study published by Perna in 2005, which again, I'll put the full study on our Blackboard site in the supplemental section. But what Perna was interested in studying was two questions right here. So first of all, what economic benefits did 1992 high school graduates who attained various levels of education realize by 2000, and what non-economic benefits did 1992 high school graduates who attained various levels of education realize by 2000? So what's important here to point out is that her population of interest is all high school graduates in 1992. So is she going to be able to collect data about all high school graduates in 1992? No, there's no way she's going to be able to do that. However, there are a number of really nice surveys that the federal government does that collects data from a sample of high school graduates every couple of years that captures these different variables. So what Perna can do using inferential statistics is take the data collected by the federal government of a sample of 1992 high school graduates and try to make generalizations about the population, right, from that sample data. So she uses inferential statistics. She's interested in looking at the relationship between educational attainment, right, of high school graduates, so their ultimate level of educational attainment. So did they go to some college? Did they get a bachelor's degree? Did they get graduate study, that kind of thing? And how is that related to their economic outcomes as well as non-economic outcomes? So she operationalized economic benefits as income in 1999. So the idea that that educational attainment is associated with economic benefits, specifically income. So again, operationalize this concept, this construct of economic benefits with income. In terms of non-economic benefits, that's another construct. She operationalized that with several different variables, whether or not people smoked cigarettes, whether or not they voted, whether or not they volunteered, whether or not they attended cultural events. All of those, she said, were potential non-economic benefits that could be associated with educational attainment. The example I'm going to give is the economic benefits table because these tables are just too huge. So I'm just going to focus on research question 1 as I show you how we can interpret her inferential statistics. So what she did is she used a multiple linear regression to estimate this relationship in number 1. And again, don't worry too much about how that actually happens in SPSS or whatever, but what's important to know is that that helps us to incorporate a lot of different independent variables in our model. So you can see all of those independent variables are listed on the left, and we're looking at all of those independent variables are related to economic benefits, specifically to income of high school graduates. So our dependent variable, again, is income, and all of our different independent variables are listed on the left. So what we can do is look here, right? And so we see again, there's some stars up here next to some of these variables. Not all of the variables, but some of them. And so if we look down at the bottom, again, always your tables should have a little code for the p-value. The standard in education, you'll almost always see 3 stars for less than 0.01, 2 stars for less than 0.01, and then 1 star for less than 0.05. But you should check just to make sure. But again, what we're going to do to interpret these is we come up here and we see female listed, and there are 3 stars there. So that means that there's differences between females and male in our dependent variable, which is income in 1999. So that means females and males have different incomes in the population of 1992 high school graduates. So in terms of interpreting the specific difference, I don't want to get too technical, but what's important here is to look at the sign on this little B column. The B column right here, the star column, the number over here, the 0.003 gets at the p-value, the stars. So those two are together here. The standard error represents the p-value, so we know there's a significant difference. And then when we want to understand the specific magnitude or direction of that difference, we look under the B column here. And essentially, because we can see a negative sign, so next to female is negative 0.033, that tells us that compared to males, females have lower incomes than males do among the high school graduates of 1999. And that's a statistically significant relationship. So if we see here, there's no stars next to any of the race variables here. So American Indian, Asian, Black, Hispanic, White. If we look over here in the standard error column, which gets at the little stars, no stars there. So that means at least in the population of high school graduates in 1999 who attained a high school degree, we didn't see any differences according to race in their income. We did not see any differences attributable to race that are statistically significant. Again, there are differences there, and you'll see in this little B column, there is a negative sign next to American Indian, Asian, Black, or there's actually no sign next to Black because it's 0, but negative sign next to Hispanic. So there are, in the data set, there are differences in income attributable to race, but they didn't reach the magnitude that allowed us to say that they're statistically significant. So there's no stars there. There's no stars next to socioeconomic status. There's no scores next to test scores, which I assume is probably some sort of cognitive test score. But we do see down here, there's a star next to bachelor's degree. So that means compared to just people who were high school graduates and didn't have any post-secondary education, that students with bachelor's degrees had higher incomes. So there's a 0.19, it's a positive sign, so that means the bachelor's degree students had higher incomes. 3 stars there, so that means that difference is statistically significant at a p-value of 0.001 or less than 0.001, so we're 99.9% sure that in the population of high school graduates in 1992, their income was higher when they had a bachelor's degree than those who had no post-secondary education. So we're 99.9% sure that those with a bachelor's degree have higher incomes than those who didn't have any post-secondary education. So I know this is a lot to take in, and this is kind of unfair, but I feel as though this is a supplement to hopefully what you read in Jones and Kotler, and you kind of got some sort of understanding of what these techniques were doing and the idea of inferential statistics. I will definitely go through some more examples with you in class from journal articles. Really, the important thing about this is helping you to be able to be literate in the literature, in the quantitative research literature. I'm not at all expecting that you're going to be running these things, but I'm happy to point you in the direction of some classes to take if you're interested in learning how to do this. They're really powerful, really kind of cool techniques, but you need to be at least literate in terms of understanding how to interpret them and read them, and not have to feel as though you're reading a journal article and you just have to skip over all of these tables with stars in them. So the stars get at the idea of statistical significance, right? And if nothing else, as you're reading journal articles, what I want you to remember is, first of all, are any of the variables significant? So going through and see if you see any stars. And then also, this is a little bit more complicated, but I'll help you go through this in class with some more examples. So if you do see significant relationships, does the given variable affect the dependent variable in the predicted direction, or is the difference between the two groups in the direction you anticipated? So going back to my example about Greek students, so would you have anticipated that Greek students would have higher gains in critical thinking than non-Greek students? I was actually surprised by that finding. And so you want to look at both, are any of the variables significant? And then for those that are, is that direction of the difference something that you would expect, or is it something noteworthy? Is it something that can inform practice? And so that is the basic idea behind inferential statistics. So in class, like I said, we will definitely have time to go through your questions about both descriptive statistics, which is important to have in mind if you're going to be doing a quantitative project for your applied project. You're not going to be running these inferential statistics, obviously, but you should have a good understanding of frequencies and means and standard deviations to be able to report the results of your research project if it's going to be quantitative in nature. And then also I want to be able to answer questions about this lecture, about inferential statistics and multivariate statistics, as well as what you read. We'll have some examples, we'll have some more examples of reading quantitative studies and interpreting these tables, as well as I have some proposals that were submitted to ASH and AERA that we will be critiquing.